Hello, this is Gregor Kapler. Welcome to the workshop on parsing and brokering messages with CombinedParser. It is a pleasure and an honor for me to have this workshop on the CombinedParser package, and I hope technically everything will go nicely now. Oh, sorry. First technical hiccup. Let me just close this. Okay. The package CombinedParsers, I had it introduced last year briefly in a 7-minute talk. So today I'm glad to get a little bit more into details and demonstrate developments that have been going on. Meanwhile, I put the link on the materials in the chat on YouTube, so you should be able to access that. My name is Gregor Kapler. I have been working as a psychometric scientist and as a programmer. Currently, I'm independent. I have always had a focus on text as a material in psychometrics, and I have done have been involved with parsers many times in my life. So I wanted to actually hide all this. So this is the first example here of CombinedParsers, which will allow you to define how to decompose strings or actually vectors of binary bytes into any type in Julia. In this example, you have a convenient syntax with pairs of symbols and then parsers as the second in the pair tuple, which will then, if you call it on a string with the speaker, Gregor Kapler, psychometric scientist and programmer, decompose it into a named tuple. So what's parsing? Parsing is basically converting vectors to any type with Julia. Are Julia types cool for parsing? I think so, and I hope in the course of this workshop I will convince you that this is actually true. The workshop questions are whether they are the types and method dispatch actually are the crucial piece of technology in Julia in order to enable this, for converting it to anything in a fast way, and extending from that whether Julia would be a good idea to build an efficient string or message processing system. So the outline is a proof of concept for a message broker, a little bit similar and inspired by Kafka. And then I will go a bit more into detail about writing recursive parsers with CombinedParsers. There have been a few questions in the community on GitHub to go more into detail about this. And then in order to contribute, to welcome more contributors, we will go a little bit into CombinedParsers internals, with looking at states and optimization. So for the first part, is Julia good for message brokering? Julia is established today, I think, in distributed scientific computing. It has been doing one of the most impressive large-scale distributed computing projects with, for example, the galaxy clustering, I think. The parametric types are really very interesting for compiled parsers because the parsers comprise quite complicated parametric typed objects that leverage the compiler of Julia perfectly. Julia has a growing adoption, but what are the opportunities in industry at large? Again, if you want to follow the workshop, you can download from GitHub or check out GitHub. Please, I'm very sorry, use Julia 1.5 as the Julia kernel. Julia 1.6 has given some issues on my side when I'm having sequences of parts, more than 10 parts in the generated function and crashed the system. This is not yet completely resolved, as I guess for you it has been similar as for me. The last year had many unexpected things coming into life, so I didn't have as much time as I wanted to put into CombinedParsers. Please, if you want to follow, update CombinedParsers to version 0.1.7 to be on the safe side. That is the version that I'm using here, and it's published today, actually. So let's get into the use case example, web server message brokering. So the big picture is that regarding business opportunity, event streaming is big business. For example, Confluence, major company, is using Apache Kafka, and Apache Kafka is basically the elephant in the solution zoo on event streaming. Not Hadoop, but again, it's a Java solution, meaning that Kafka inherits the same issues like all Java systems regarding the Java virtual machine and its overhead, as well as some properties of the language. So basically all transformation and all kinds of describing how messages are to be brokered and passed on and transformed will require Java classes to be programmed. And the big question is, are Julia types of method dispatch suited to build an efficient distributed message broker and parser? Regarding the prospects, this is the benchmarks from the CombinedParsers regex package, which is providing a plug-in replacement for the PCRE C library regular expressions used in Julia when you're using the R string macro, which shows you that the CombinedParsers recomp is actually, recomp is actually the constructor for the CombinedParser regular expression part, and you can see the benchmark is competitive with the regular expression benchmarks. In that plot, you can see on the y-axis the nanoseconds of the matching and the constructing of regular expressions with CombinedParsers, and on the x-axis you see regex, and you can see in green all the test cases, which are from the PCRE unit tests, that about 59% of the cases are actually faster with Julia CombinedParsers. So from that perspective, I think the prospect looks quite good, because Julia is, with the parametric types and the strong compiler, in a competitive position to create message processing, string processing in a very fast way. And putting that together with more infrastructure for message brokering in Julia might be a good idea compared to Kafka based on Java. So maybe you know Kafka or are interested in Kafka. I will briefly describe the Kafka terminology and the parts that we will follow along in this workshop. The major term is a message broker, which consists of a producer and a consumer. The producer sends data directly to the broker. That is the leader for the partition without any intervening routing tier. That partition and the routing we will leave out of this workshop, because Kafka, which we will see in a minute, has strength in concepts about the streams and persistence. The consumer works by issuing a fetch to the broker. So it's getting it from partitions in the case of Kafka, which we will skip here. So how can message broker processing be done in Julia? Again, from the design of Kafka, there is the question about push versus pull. So how do you, from a high-level design, construct your message flow? And from the documentation in Kafka, you have an initial question. We consider this whether consumers should pull data from brokers or brokers should push data to the consumers. In this respect, Kafka follows a more traditional design shared by most messaging system where data is pushed to the broker from the producers and pulled from the broker by the consumer. And this design is actually exactly one and the same as Julia remote channels. It has the same design, it's compiled and it runs distributed. So in that sense, regarding the consumer and the producer part of message brokering, I think Julia has a very strong ecosystem already there. So we're using distributed. There is a, it's actually following along quite well from the Julia manual, the asynchronous programming. And we will look at an example of web server logs, which we will use in a remote channel. So to summarize, the POC focus here is distributed and compiled processing and parsing. The limitation is there is no stream persistence in remote channel. We will discuss that later at the end of the example a little bit more, because I think this might be an interesting extension actually to remote channel if this kind of persistence and indexing would be available. I'm using some web server logs from the Elastic stack. Elastic is also a Java-based software, which is very prominently known database with a strong focus on text and is often used in combination with Kafka. It's kind of a natural match. If you want to follow the workshop, please remove this false and download the 2 files. I already obviously have them here. The producers, in this case, will read line by line, parse a name tuple, and then replace the IP in a transformation with a GUIP. So that's the plan for now for this example. So the first thing I did is I copied base each line and adapted it a little bit such that it doesn't close when it reaches the end of file. Because when you're actually producing from an Apache log file, you obviously don't want the file to close and rather wait until it is appended to, so you can read the next entry. From the distributed computing manual in Julia, we can basically adjust this example, the example rather straightforwardly. So the first thing is you will put the lines into the broker in a for loop. So you have this iterator, each line follow. So let me just, if you're new to the iterate interface, let me go through this a little bit more. So this structure is basically just keeping a handle on the stream. and then some undone function, which probably I could have removed here, because typically it's calling close when the stream is done in the each line base implementation. And then we have a waiting period, which I set to 1 second, and then we have the iteration function, iterate function, which is called in a for loop. The first element in an iteration is received by calling with just the iterator as an argument, so the state is nothing here. And then it will be returning it, or Julia is expecting the iterate function to return a tuple with the element that the current iteration is returning at the first position, and the state for retrieving the next element in the next call to iterate in the second position, since this iteration function is not handling state other than within the stream. As with its position, the state is here kept as nothing. Then an iterator will give you, or will provide, an L type, which in this case is a string, because we are reading the lines within a file. So these will be a string, and the iterator size is unknown because we don't know how many strings are in a file, especially in these files that do not close. The everywhere macro just makes sure that your definition is executed actually on all the processes that you have. Let me go up there. Edit as worker processes here. So it's used by distribute to pass that piece of code to all the Julia instances on all the processes, and making the function defined everywhere, so it can be used. The remote channel API has basically two major functions. The produce and the consume function in Kafka are mapped to the put function for the producing, and later we will see the take function for the consuming. So in order to put the lines of a IO open file to a broker, we're just putting each line in the file to the broker, and I use the spliced argument A in order to create a tuple here, which is convenient for actually passing on the file that we have read the line from. So you can see here, if we're using method dispatch here heavily, the next function is just opening a file and starting that put lines on the IO of the open file, the IO object of the open file, and is passing actually the file name as an argument here. So actually we will get log lines in that format, in the sense that we have one line in a tuple at the first position, and then the file on the second position. And then we can use the async command in order to just issue those put lines functions to a thread in the background, and it will listen to the file and receive the logs line by line and put them on the broker, which we created before, which is the remote channel here, web server logs. So when you take, this is the take command for consuming a web server log. So you can see logline, source is the web server log. So you get a line, and then you get the file name actually that we got the line from. The workshop is not focused so much on the distributed capabilities of Julia, but the manual on the distributed computing provides you quite detailed information on how to customize your web server logs, your remote channel. It's caged, so you can basically determine the size of the cage. You can restrict the types that can be put on the web server logs. By default, we are just using any kind of object, so we have no type restriction used here. While we actually could have used a type restriction here, because we know it's a string. The line is a string, and the file name is a string, so it's a tuple of 2 strings. Now let's get into the interesting bit. So this is basically now, this has only been infrastructure, how to connect to files and how to put the files line by line into a remote channel. This is a very simple example. Another example that I successfully did at some point was downloading a Wiktionary dump for the German Wiktionary, which is an XML dump with parts of the XML being wiki text format. So, and the dump is GNU-zipped or BC2, I don't know which kind of compression they used. So you have a stream, and you can use an XML stream library for parsing the XML out, getting the data that you need, like the title and then the wiki text part of the entry, and push those on a remote stream and parse Wikipedia pages in a distributed way. A combined parser package, by the way, and we will have a link later, but there is a combined parser package for wiki text format. It seems quite complete, but it's not formally tested, because Wikitext, I think, doesn't even have a formal language definition, syntax definition. All right, so let's get into the transformation. So the consumer, in this case, we want to take the lines from the remote channel, the events as they are called in Kafka, and produce parsings, similar to Kafka, where these are called connection transformations. And the parsings will be done with combined parsers, obviously. So the first thing, let's look again at the at this one. So how is a log line built? It has an IP in the beginning, and then here we have 2 dashes. We will see these are actually omitted IDs for a device and a user. Then we have a date, and then we have the HTTP method and the path, and then we have the HTTP version, the status code, the size, and I'm actually not sure what this later dash is, but then you will have the client ID at the end. So in order to parse that out and change basically the IP in the end with the GEO IP, we first need to get some numerical parsers. So combined parsers can be combined, that is why it's named like this, with text parse. Text parse is providing fast methods that have been customized for CSV parsing, and Julia, I think, is currently the fastest language for many CSV parsing tasks. So text parse for numeric types, I guess, is quite optimal. A note here, in the previous version to 1.7, the class architecture has been such that combined parsers inherited from the super abstract type in text parse, which is abstract token. And I removed that inheritance because, yeah, I wanted a root type in my package. It seemed like a better idea. Since then, in order to use the function call on the object, on the parser object, you need to wrap it in parser. If you don't wrap it in parser, you will get an error because text parse does not support to be called, while oops, a combined parser can be called. Also, you can use the text parse package for parsing date and time tokens with flexible formats. This is also quite established and it's great to use. And then you can see here in the lowest line that you can use CombinedParsers objects are callable with a string and then return the result here. Of course, in these two examples, all the work is basically done by text parse, and all that CombinedParsers is providing is a wrapper around it. As far as I know, text parse does not support iterating matches if they are ambiguous. So these matches are just the first match or a failed match if a second match would be required. Okay, now these, let me just see if there are questions. Can't see a link to the materials, but okay, this is answered. Okay. So the date actually is the second part, but in the log line. The first part is actually the IP address. So how can we parse an IP address? The IP version 4 IP addresses are bytes separated with dots, and the bytes are written in a decimal format. So that is why we are using text parse numeric uint 8 here. Let me just toggle the toolbar just to show you that a decimal byte of 300 would actually fail because it is larger than, oh, sorry. Of course, we are passing things and not numbers. So this is failing because the numeric needs to fit into a unsigned integer with 8-bit a byte. The IPv6, on the other hand, is also sometimes used in the log lines, and an IPv6 is actually 8 repeated hexadecimal values. There is this function integer base in CombinedParser, which we can use for this, and you just provide the base as an argument, and it creates you a parser. So let's decompose these constructors here further. So we have either a decimal byte or an integer base 16. And in the IP version 4 case, we repeat them 4 times and interleave them with a dot. So you might know the join syntax of Julia. So if you have a series of strings. Wow, sorry, I'm nervous. A vector of strings, and you want to join it with something to interleave it. You can actually use join like this, and it's we're using the join syntax on a parser. Will create a parser that is matching actually the output that is produced by join if you provide a vector of strings and a delimiter. And you can see in the output here how such a parser is constructed. It's basically a sequence which needs to obviously start with, it's the second one that is printed out here, a hexadecimal digit. And then you will have 7 repetitions of the delimiter and another hexadecimal digit. And you can see down here the result type of that IP v6 will be an array of integers. So let's look at this using benchmark tools. If you are matching it, you only get the state, which is like a tape recording the positions of the matches and the state of the matches if they should be reused, for example, to get the second match if matches are not unique. And so we can, and then with get, you will actually get the result that is created from that parser. You have seen before we have used this callable option. So just calling the parser with that, it is doing the matching as well as the get. And but you can decompose them here. That is interesting here. I will remove this because actually we don't want to get the numerical arrays for the IP addresses, because what would we do with that? We need to get the IP address as a string in order to get the geo IP location. So what we're doing here is we're using the exclamation mark for capturing the matched substring without doing the conversion that is by default constructed with this join function. So we are basically overriding the result type that is returned by join, and we're actually allowing any of the both possibility IPv4 and IPv6, and whatever it is that is matching here with the exclamation mark, we're using a class that's called join substring that is just returning the substring for that match and is actually skipping in the get process the construction of the integer vector, which leads to quite some performance gain. If you see here, if we're using the match of the IP, which is actually a more complex parser because it has either one of those two options in there, and then we call get m and take the time. We have 30 nanoseconds for the substring, and we have 8.5 microseconds for the array creation. This exclamation mark is actually has been inspired by Scala fast parse. I took it because I actually liked reading the fast parse syntax with that. Some users have found it confusing. I'm still open for syntax preferences from the community, of course. Especially since you can also write a double exclamation mark, which is not a negated negation, but rather you can see here, this is first converted into a substring, and then the string is interp, which is very useful if you want to parse large amounts of data, for example, a Wikipedia archive or something like that, and break it down into a lot of words that are basically repeating many times. Then you can use the intern strings package capability to intern strings, which is highly recommended over using just the substring if you're parsing large files. Because if you're using substring, the original string that the substring is a part of will be kept in memory and will not be given to garbage collection, and your system will crash. I like the syntax quite a lot because it just means, okay, make this a string or make this an intern string. But I understand that some people find this confusing with the negation operator. So feedback appreciated on that part. Let's actually keep this. Okay, let me see. Are there any questions so far? No. So far we have defined parsers without, this should be macro, without the syntax macro. The syntax macro is a convenient macro for defining a parser with a name and storing the name as part of the parser itself. So there is a type which is called named parser, and with name is actually creating such a parser with a name. And the syntax macro will just use the variable name in order to pass it on as a symbol to that named parser. And also the second thing that this convenience macro syntax is doing is it is creating a custom parsing string macro, so name string. We will use that now for Apache logline because now basically we have everything ready. We will define a few more helper parsers, one general integer parser, because we have this just for a byte above, and in the logline we have integers that are larger than a byte. Then we want a no space, which is just some repeated characters that are not a space. Then we have some escaped quotes, which is just in order to show you how escaping can be done easily and dirtily here, because in this case, the either is either an escaped quote or something that is not a quote. But the escaped quote would be retained in the parsing itself. If you want to see how escaping can be done in such a way that the escaped character is actually transformed into the proper UTF-8 character, you can look at the PCRE regexp implementation within CombinedParsers. It has obviously some performance cost to do such a thing, because in that case, you need to cut the string apart into character by character to character transformation, and then recombine them into the final result. So let's look at the full Apache logline here, which is actually the same format as for Nginx. So we will spare some time here, as we only need to define one syntax. It is using the sequence constructor for constructing just a sequence of parsers that can be provided with a symbol pair like this. And in this case, if symbol pairs are part of the arguments to sequence will by default transform the result into a named tuple that is just retaining the names, the symbol pairs in the final result and omitting everything else. This code is convenient. It's not perfect in the sense that it's not optimal speed. If you want to do a similar thing, you can always do create a custom transformation instead of creating a sequence like this. Let's look at, well, let's go through it. So we have the IP, then we have an identifier and a user, which is basically no space or a dash. And if it is a dash, we actually replace the matching dash with missing, because that might be nicer in storing that in a database or a CSV file. Then we have the square brackets and then the date time and a time zone with a number. Then we have a quote, the request methods, which is either get, post, head, and options. At least those have been the cases that have been in the log files. Then we will have the request URL. And then we have HTTP/ and then the HTTP version. Then the status of the request and the size of the delivered content. And then we have the URL, and finally the browser or the client, actually. So maybe I will just, here's a better term. So if you execute that, you can see quite a long display of how this parser is structured. So the output is organized in such a way that well, it's a tree. The parser is a tree. And each line will start with the constructor. And if the constructor is actually wrapped in several result transformations, you will see them here with the pipe operator appended in the same line. So this sequence is mapped to the ntuple function, which is creating the named tuple with the pair keys as names and the parsing results as values. And you can see this sequence has the name Apache logline because of that syntax above here. So then we have our IP address syntax here, which is again using join substring and intern, and then actually mapping it to a string because the intern type inference returns an abstract string for some reason. And yeah, if you have just a character, you have no constructor given, so a dot, or sometimes you have the regular expression, PCRE regular expression representation for especially character ranges, jar in or jar not in. Mapping to constants is represented as pairs, just as you can write them in the parser constructors. Sorry for that one. I need to rewrite the print constructor function for it. Yeah, so it's actually, I think, a quite nice way to look at parsers. At least I find it very convenient to understand what is actually going on in a parser with that kind of functionality that is collapsing several levels of the hierarchy with pipes if it's just wrapped and has not multiple children, and putting the children down there if there might be misunderstandings. Down there, you can see the result type, again, of this complex line parser, which is just as you would expect it. You can just inspect it here. You see you have the tuple, so the values of the name tuple, and they sometimes have substrings and sometimes have strings. So let's just fix this here. So, well, actually, I think we can fix this once and for all here, and once and for all here. And let's see. So now you have strings and union missing strings, which is exactly what you want to have if you want to store it. The logging is can be switched on if you use the callable type of a combined parser. So you have the Apache logline is the parser, the logline is the line that we have taken before, which is now something else, I think, and the thing that was displayed here. And you can provide a keyword argument, which might either be a vector of symbols, so it will log just those names that are actually listed in that vector, or you can log fully with log equals true, and you will get all the matches logged for all the names that are within the parser, defined within the parser, which for that parser we had here mainly comprises of the keys of the symbol parser pairs within the sequence. Okay, so this is the parser. Now the next step will be to use this function in order to transform our messages in the message broker, so to connect the remote channel where the Apache, the log lines have been, and put them into a remote channel with parsed results. So the channel we had so far, the web server logs, had just tuples of lines within the log file and the log file name. And now we actually want to change that in order to contain the parsed result. So we have a function Again, using multiple dispatch for later to connect things quickly. So we can parse a logline. We have event and file, so we use the tuple decomposition, argument decomposition here because we have tuples in our remote channel. The parser and the producer, we create a new producer which will get the results. We're using here the try parse function. So if the parsing is not successful, we will get actually a logged attempt for the parsing. So we can fix if something is wrong with our parser for a certain event, we can log that somewhere. In this case, we're just logging it to standard out. And if it is successful, so try parse. If it is not successful, we'll return nothing. And if it is successful, we will return the result type of the parser, which in our case was this named tuple. And that will be put on the producer remote channel. So we will have a remote channel for log table rows, because named tuples in Julia can be straightforwardly used as rows in the table ecosystem. And let's just try this out with parse logline. With the logline we have taken from the remote channel before, and you can see it is just returning again a tuple, and the first element of the tuple is now the parsing result, and the second part is still just the file name. How can we connect this now? I mean, in Kafka, you would have a lot of configuration to do. You would write not just a function, you would write a class, and then you would register the class somehow. What we are doing here is we're using a very nice function with argument passing on to a function argument, which is only possible because Julia has such a strong focus on functions as first-class elements within the programming language without any performance performance degradation. So takemap will basically take a function which is taking the event that is taken from the broker as a consumer. So we're a consumer of events and messages within the broker. We're taking the event from the broker. And then we're calling the function on the event and just passing all the arguments and keyword arguments on in order to be very flexible to pass, for example, the parser and the channel that we produce parsed events to, in this case. So we would then have the option to issue an asynchronous process by calling this takemap, which will run forever and sleep when the broker has no events in the queue. And as soon as the broker has new events that can be consumed, will continue. And in this case, we are passing the map function parse logline, which was, you can see, taking a tuple, logline and source, which is exactly the stuff that is coming from the web server logs broker. And then we use the arguments Apache logline and log table rows in order to provide the consumer. In this case, we are a consumer of Apache loglines and a producer to log table rows. Correction. We are a consumer of web server logs. We're parsing what we consume with Apache logline, and we're producing the result to log table rows. Okay, now we're going to put a second transformation. Any questions so far before I go to the geo? 5 new questions, sorry. Oh, sorry, okay, let me see. I see. About the exclamation mark versions being faster, is there a catch there? Any downsides or limitations to it? So, I mean, the downside is that if you want not a string or substring as a result, but need a complex object, that is obviously a downside, because otherwise you can parse it in a second step, but typically that will be slower. Other than that, there is no catch. Depends on what result type you want. It's just a transformation. Have in mind, substring is really fast, but has the downside of keeping a memory handle on the original string. So there will be no garbage collection. And the double exclamation mark has the downside that the interning of the string will require a dictionary lookup. But that is in Julia very fast. Yeah, and it will lead to less memory consumption. So then we have another question. What would be the equivalent to the regex \s includes tab? Yeah, that is. Let me show you that right now. I mean, we'll get to that later, but I think it's answerable very quickly, because there is this regex package, and if you're using that, you can actually that is a replacement. So the replacement is the thing itself. It will be a bit slower now because it needs to be compiled, but you can use basically just the regex syntax with the RE string macro, and get a combined parser from it that you can integrate seamlessly within the other constructors of combined parsers. Okay, next question. Without the exclamation mark, the either returns an array of integers. Would matching against that mean parsing individual ints and matching? Is that why the substring version is faster? Okay, that is a good question, but needs a little bit of decomposing the question. Typically, if the either would return an array of integers, wherever that part of the result is used in an outer parser, would just contain an array of integer. Okay, this is still running. Meaning, but I can still show it. Let me go up there. You can see here, the IP address is the string type in the name tuple, right? And if you would not use the exclamation marks, you would have a vector of integers in here as the result type used in the outer parser for that part of the object, the name tuple in this case, that is produced by the outer parser. But, and that is why it's a good question, you can parse individual ints, if I'm understanding the question correctly. I mean parsing individual ints and matching. I mean, the parsing of the individual ints it depends here. So there are two ways I could read this question. One way is the IP here parsing 2003 first, and then EF second, and then that second, and each time creating the result. That's not the case for this example with the IPv6, because the IPv6 is using, you can see here, the X digit char in repeat. So it's basically matching character for character, checking if it's a hexadecimal number or a character, and if so, it proceeds in the repeat, and then in the end, it's just taking the substring. On the other hand, if you're looking at the IPv4 part, you have this unsigned integer 8 here, which is the text parse.numeric parser, which is actually parsing the number. So it depends. It depends. That is one way to read the question. The other way to read the question is, but probably you didn't mean that, if you want to parse the vector of integers apart from that. And that's actually possible if we have time. I can show you a Boolean parser, so you can actually parse not just strings, but byte arrays too. Okay, next question. What does the output of the exclamation version look like? How performant is it? Okay, let's see. Okay, the performance thingy was, okay, let's just, this one has been from the substring part, and yeah, the interning takes quite a bit of time compared to just the substring. So 30 nanoseconds for the substring, and that is nearly 20 times as long for the interning, 500 nanoseconds. Okay. Yeah. Okay. There was this other question that is actually ready, that we have been here. So you can actually use this regular expression. So see that it's matching space or top. Okay, just to be clear, the reason we want to copy a file stream contents to a remote channel is so that we can process the stream in a distributed way. Yes, that is right. That is right. Well, and actually you're very flexible with remote channels in Julia. You can, I don't show this here in the work, in this workshop, because I'm just using asynchronously without specifying where I actually want that process to be computed. But you can connect to remote machines, and you can use the multiple processor cores on your computer, and you can assign computation to very specific remote computational resources. So the question would be, yes, we want it to be distributed, and second, we might also want it to be channeled in the sense that we want to use a remote machine and dump, for example, so a consumer on a remote machine that write into a file on that remote machine, for example. Okay. I think that have been all the questions. So comments allowed. Okay, good. Let's continue. So the geolocation, I will remove this one. I'm actually using this GeoIP lookup program, which is a Linux program. I'm on Ubuntu. So if you run that with an IP argument, so these backtick quotes in Julia create a system command, and you can pass it to run, and then that is basically exactly the same as if I would run this in the terminal. So you can see here I have a country edition. So this is my IP a few days ago in Germany, but the city edition does not contain city information for German IP addresses, obviously. But if you're using the 8888, I think that is the DNS server provided by Google, you have country as well as city provided, right? So we want to use this external program in order to now transform our parsed logline in such a way that we replace the IP address with the GeoIP information and actually delete the IP address for privacy reasons, because, for example, in Europe, it is not advisable to store all the IPs in your log in a database for privacy reasons. And so these need to be removed often in processes like log processing with Kafka and message brokering in that sense. So what we're going to do, let me go back there. So we have this output of the GeoIP lookup, and that is actually we want to use the city if it is there. But if the city is not there, we don't want to use IP address not found as the result. We actually would like then to use the country edition. Since the order is such that, well, we can only determine if we need to use the result in the first line after we have read the second line, we're using the either constructor. And we either have a sequence where we have the GeoIP country edition as a prefix, then we have inline and newline parts, which is the country name here as the inline and then the line break. And then we have the city edition part. And actually, we only want to match, sorry, I will put that down here. Continue matching if we don't have this IP address not found. So we use a negative look ahead here, and then we're using the inline and another new line. And the sequence constructor allows as a first argument a transformation argument. Transformation argument are numbers and functions. This might not be optimal going further into the area of parsing arbitrary vectors instead of strings, sequences of characters, so sequences of integers. If you would parse sequences of integers, this might actually lead to some confusion. Another way you can do it is, let me just put this here, is you can actually use the getIndex command on a parser if it is a sequence, and it will create a parser that contains a transformation to retrieve just the second element of the match, which is in this case this inline. You have seen above using named key value pairs here in order to create a named tuple. this indexing with numerics is the fastest way to do it. Yeah, so, and then we would have a GeoIP function where we provide an IP address as a string, and this would just construct the system command substituting in the IP and read it as a string and pipe it through to GeoIP lookup out, which is the parser. And since the parser is a callable, this one will actually give you the parsed results from that command. There is another issue, however, because GeoIP actually does not support IPv6. So actually what we're doing is we're reparsing the value of the IP address that is in the name tuple, and if it is actually an IP v4, we map it into GeoIP, and if it is an IP version 6, we store that we have no GeoIP for IP version 6. So let's try this out, and maybe let me just, for the sake of it, fetch that IPv6 address from up here. So we can test that too. Oh, wow. Oh, yeah, of course. Sorry. We're calling the function here. Actually, call the parser here. So now you have the proper result. So this one is again parsed with the country. This one is again parsed with the detailed location. And then the IPv6 will get the error message. Then we're using method dispatch again. In this case, what we're doing is we're defining a GeoIP function for a named tuple. So again, we're using dispatch heavily here. We had this GeoIP function for a string, which is issuing the system command. For the named tuple, we're just sloppily assuming here to have an IP address or an IP property in the named tuple, which is obviously not always the case. And we are issuing that through IP lookup and storing it as the GeoIP property in a new named tuple, and then all the other property names, if they are not the IP, will just get reproduced in here. So let me move this up here. So you see, if we provide just any named tuple with something else, you get just the IP replaced with the GeoIP. All right. So basically now we're doing the same thing again. We have this log table rows remote channel that is basically a message broker. Now it's containing named tuples with IPs. And now what we want to do is we want to consume all the entries in this log table rows and produce modified entries with the IP deleted and the GeoIP inserted into a new remote channel, which we call GeoIP rows. And we're using, again, the same function, takemap. Now the mapping function is GeoIP. Let me go back here again. We have used here a multiple dispatch again. If we call it with a tuple, as are our entries in our events, because they're using this second value for the file they have been coming from, which we could obviously handle differently too. We could actually have put them into the name tuple as a property if we would like to, but I decided to do it like this. And if we provide a producer too, we put it to the producer after calling GeoIP just on the name tuple, and on the name tuple we had discussed that before. So basically what we have here is takemap. The input that we are consuming comes from log table rows, and the channel that we produce to will be GeoIP rows. And if we are taking an element now from the GeoIP rows, you will have the desired results. So let me see if there are any questions. No. No. Okay, so I think this example has shown that the remote channel can be mapped very conveniently with any Julia function, just by issuing this asynchronous take and map, where the mapping function will put some transformed result on the remote channel that we need to produce to. Obviously, within these functions, you're free to do what you want. You can store in a database, for example, with Lighthouse.jl, or you can write out into another log file. You can dispatch it to multiple consumers if you handle messages or transform into values of different types. You can use dispatch to branch channels. You can also dispatch in the sense of copies very transparently. You just write the function that does exactly that and plug in the function in the takemap call. As I will, for time reasons, not show the consumers here. One thing that I initially planned to do, but I wasn't getting ready with the Git tree JL, was that I wanted to put it there with CSV files, which would basically, the workflow should have been there with Git tree, that you create a folder with the file name of the log file initially, and then different CSV files within that folder, depending on the request method, for example, and then issuing commits after a certain number of consumed events. I will publish the Git tree JL, but will not go into details here for time reasons. Okay, the parallelism is just very useful and great for parsing. I mentioned that before with the wiki dictionary parsing on a, I think it was a 16-core machine, and it was just, yeah, I mean, instead of waiting a day, you're just waiting less than an hour. It's nice. So this concludes this proof of concept, and I will then go on into detailing a little bit more of the various constructors that are there. But the message brokering proof of concept, I think, comparing Julia with Java, I have extensive experience with Java from my previous life, nearly a decade. And considering to write Java classes for Kafka transformations seems to be really painful and cumbersome, while writing this workflow in Julia is quite slick, especially, I mean, from the perspective of dev time in that case. but also in this aspect of runtime, because PCRE was the benchmark used to compare combined parsers performance against, and PCRE is written in C and is among the fastest regular expressions libraries out there, surely faster than Java implementation of some parsing and processing of events. Also, the concepts, I think, are much clearer in Julia, thanks and due to multiple dispatch and this functional nature of the language, as well as obviously parametric types that are used in multiple dispatch. Because actually what you want to do when you, or what are we talking about when we're talking about message brokering, is a processing flow, and that is a functional flow. It's a composition of function and not natural for classes and object-oriented programming. So I think from that perspective, Julia is a great candidate for message brokering. So there is prospect, but there are limitations, obviously, because we have skipped an important part of Kafka. We have just focused on processing now here, but not handling, event handling, and storage. And this is another quote from the core concepts of the Kafka documentation. A stream is the most important abstraction provided by Kafka streams. It represents an unbounded, continuously updating dataset. A stream is an ordered, replayable, and fault-tolerant sequence of immutable data records, where a data record is defined as a key value pair. So serializing messages with offset indices in order to make it replayable and fault-tolerant. So just imagine the consumer is going away and is restarting at a later point. Obviously, if you're not fetching the messages or taking the messages, they will not be available, or they will remain available. But if you have multiple consumers, that might become a problem. I think probably something like that should be possible, maybe with mmap or mempool, maybe with a key value store. That would be an interesting feature, I think, for Julia remote channel, to make the remote channel persistent and replayable and fault tolerant thus. Currently, this, for the implementation of message brokering in Julia, this would surely be a deal breaker, because the system as it is now cannot provide any processing guarantee, at least not until Kafka events as part of topics or partitions and this replayable nature of streams in Kafka are addressed. Okay, this concludes this part of the workshop. Let me go to questions and see if there are any questions. I don't think so. Okay. Okay, then let me switch to part 2 for a walkthrough constructors and an explanation how recursive parsers can be created. So the first part of this will be rather speedy. I will check the questions repeatedly. So if you have any question regarding any of the constructors, please ask. But I try to walk through the constructors in a very speedy fashion. It is basically the Julia documentation system is so great. I think most of the constructors are quite well documented now, but there always is space for improvement. So any char is basically matches anything that it's looking at and is returning the value at the at point. So this would be the dot in regular expressions. This will be renamed because it still has this any char. It will become, well, there will be a deprecate alias, but it will be any value because similar to char in and char not in the value matchers. Since we successfully applied combined parsers already to binary data in BSON, and these names now don't catch the general semantics anymore. So char in are value matches. Value matches technically are using function isMatch that you can override. So you can provide custom types in order to check if a value is in if a predicate is true for a value. So the provided possible types that are detected is the colon, so the unit range on characters. Strings are also supported. So, I did some testing in both cases, the unit range as well as the strings. I'm putting them into some dictionary-backed lookup because it is just the fastest. But what's interesting is you can also use functions, predicate functions, and you can use Unicode category symbols. So just like in PCRE, you can also use Unicode categories to match with \p. So yeah, you can see you can match letters or uppercase letters or numbers. The match semantic is the same as with the match semantic with PCRE, regular expressions in Julia, meaning that it will search in the string that is parsed for the match. That is different from the parse semantic, which will not search, but assume that we're starting at the beginning. The character matches respect Boolean logic, which sometimes is nice. So you can have char in, and char in, char not in, if you want to combine those. This is probably not very relevant for you writing your own parser in that semantic, but it is very handy when you write a parser for a different parser language. So for example, the parser for PCRE regular expressions is written as a combined parser, and then is creating combined parser constructs from the PCRE notation. And in these cases, you sometimes have these nested things occurring. Char not in is same syntax, but inverse negated semantics. The Unicode classes are documented too. So it's, I think, the full set of Unicode classes that is supported by PCRE at least. Then there are these internals, which is this isMatch, which is an outer matcher because sometimes characters need to be masked or forbidden in PCRE with the extended syntax and things like that, so I needed that. But the major logic is done in underscore match, which is just quite straightforward. The repeat syntax is, we have seen that before. It is just similar to what you would expect from the repeat syntax to have. You have the minimum number of repeats and the maximum number of repeats that you expect. The default is a minimum of 0 and maximum, I think it is 1,000. Let me see. No, it's actually a million. Also, there is a convenient function, repeat one, which is the plus sign in PCRE, regular expressions. Most of the constructor functions allow you to have a function argument in the beginning as an abbreviation for mapping the parser through a transformation. The optional parser matching is there with a little bit of a different syntax, different to repeat either 0 or 1 times, because it replaces the result with a default value if you have 0 matches. So for example, here you could do something like this. You could do optional matching of A, but the default is 42, and because that's the default answer, isn't it? And then you would actually, if you create such a parser, which is, I think, a nice thing to actually look at here, you can see the type inference is figuring out automatically that you're having a union of either an integer, the default, or the inner parser. Lazy is a constructor that is also there. Let me just briefly look at the questions. Lazy repetition has the same semantics as in PCRE, regular expressions, with the question mark operator or suffix following either a repetition or an optional. So for a repetition, it means it's not matching greedily, but lazily. And for a optional, it's also meaning that the first match will be no match, so the default value, and then the second match, if you're iterating to the next match, will be actually the inner parser of the optional. Very convenient, in my opinion, in my use of the package, have been repeat stop and repeat until, using negative look ahead, because that is actually a pattern that is repeating quite often, meaning you want to repeat something until a certain character, and then it should actually stop. So, but stop should actually not be matched. So it's repeating until stop, repeat stop, and sets the cursor before stop. So if you're looking here at the example provided, you have repeat stop any character until there is a B, and then we actually want another any other character following that repeated character until B. The asterisk is, in Julia's string syntax, the operator for concatenation, and in CombinedParser, the asterisk is used or can be used for constructing sequences too. So you can see here the repeat stop will be that first sequence, that inner sequence. So you see it is a negative look ahead, checking if we are actually at a B, and if we're not at a B, it's matching any character, and it's repeating that until it matches this B. And then the next character is stored in the subsequent anychar. So if we apply that parser to ACBX, you would have AC, and the next character is actually the B. That is a little bit different from repeat until, which will repeat until stop, actually until, but it's using it as a stop and repeat stop and setting the point after stop. So in the same example as above, this would actually now skip B. That is, for example, useful when you're matching until the end of a bracket or something like that, and you don't actually need to capture the bracket. The result in both instances is a vector of the result type of the parser that is repeated, because normally the matched character is not returned. Here, with repeat until, if you actually want to have that until character returned to, you can use the with until argument. And another thing that both functions, no, actually only the repeat until function provides is the wrapping. So for example, if you want to join substring the thing that is repeated until there has been a B, and the B is skipped, and you would write an exclamation mark in front of repeat until, you would actually match the sequence including the B, because the next part is the X. So that is the reason why you can actually pass a wrapping transformation function into repeat until. Let me see if there are any questions. Yeah, there's a question. One new question. How do we specify that the whole string has to be successfully matched? That is, if we want parse optional A, B to return false, since B is in the string is unmatched. Okay, good question. You would, we will get to that in very bit. Let me defer that question a bit, because that is to do with assertions. So we will get back to that when we are at assertions. You have already seen the join function, which is mimicking the join function of base Julia, as I have explained before. But this function now has the last delimiter can be separated, so you can have join apples, bananas, and pineapples with a comma, and the last one should have no comma but an and. That is not yet supported, but I like it, so this should go in there too. The supported features of join, it's delicate if you want to use infix and prefix. We will have an example later why these might be useful. But by default, if you don't have, if you don't use this infix argument, basically you will get a result type just the same as this repeat, meaning a vector of the result type well, a vector of elements of the result type of the inner parser, the repeated parser. Just like here, you join any character with comma, so you will get a 3-element array of characters, A, B, C, and the commas are eliminated. However, if you want to have the infix, the delimiter, stored in some way, because sometimes, I mean, in this case, it's trivial because you have a constant parser of commata, but this might be an arbitrary delimiting parser. And in that case, sometimes you would be interested in getting the parsing result of that. And that is the case, for example, with operators, as we will see in the example later. And if you put that as a prefix, you can see that you will get actually the first element singled out, and then in a tuple as the first element in the tuple. And so the first match is the first element in the tuple, sorry, and then the consecutive matches will be listed in a vector of tuples with the delimiter and then the other matches. And for suffix, it's different. So prefix is prefixing the delimiter, and suffix is suffixing the delimiter in the parsing result. Obviously, you don't, I mean, you can just try it. You will not, the type in front of Julia is so beautiful that you get all of these types inferred automatically, obviously, right? Okay, let me see if there are questions for this. No. So atomic is another constructor that is rather useful if you want to prohibit the parser from matching, well, basically backtracking. So you're having a parser, and a subparser is getting its first match, and then subsequently in the parsing process, you get into a dead end. So you're having the backtracking of all the parsing tree, trying to figure out next matches and trying to complete the parsing. And that means you, for example, that is used when you're using parse all. Parse all is really listing all possible parsings. So for example, here, if we have a sequence of 2 repeats of anything and apply that to a 2-character string, you obviously get, in this case, oh, that is an, okay, let's reply to that question of the complete thing here, because it's offering itself. So you can see A and B in the first repeat and an empty second repeat. 1 in each, just A in the first, an empty second, an empty first, both in the second, and so on and so on. So you have 6 possible matches in that AB for that parser of a sequence of 2 repeats. But only if you don't require this to be complete, right? So the match might, or the parsing might abort early. If you don't want that, if you want to really consume that to the end, we will get to it in a second. You can just add end to the sequence, and this assertion will check that it's really just valid if the parsing stops after B. And then you obviously only have 3 possible matches. But if you think you don't want to backtrack into the first match, so the first match greedily matches both, and you don't want to backtrack it trying to match to continue after matching only 1 or 0, you can actually wrap the repeat into an atomic, and then this will be prohibited. Atomic is also available in as an atomic group in regular expressions, and I actually forgot the syntax, the regex syntax. Yeah, it's brackets question mark greater than, and then the regular expression. Then the sequence, we already have seen the sequence. Let me see if there is a question for atomic. No. So I mentioned, well, let me mention here, the sequence has, well, parts which are parameter, it's a type parameter, and typically the parts are stored in a tuple, so it's immutable and can be compiled for optimal performance. But in theory, it could also be something else that is indexable. Then the state is also a type parameter, and you have actually the option in the constructor to determine what kind of state you want, if the state cannot be simplified. So, for example, sequence is smart. Sequence checks if all the parts are actually very simple parsers. A simple parser is a parser with just a match state. So it's either matching or not matching, like a specific character, or even a character a character matcher, like a char in. It really doesn't matter exactly. We don't need to record the state of a matching character because we can just look it up at the position we are currently at. So there is this singleton type match state. And if all parts have the singleton type match state, the sequence is only matching if and only if all the parts are matching in sequence. So the state type of the sequence could be a tuple of match states, or is reduced to actually use just the match state. The sequence result type is typically by default a tuple 2. You can override the function sequence state type or sequence result type for a certain type of parts and customize these, but you might need to implement the iterate function and maybe the get function in that case too. We will see a little bit into the internals later when it comes to lazy access. I mentioned that already, that sequences can be also created with the asterisk, like in string concatenation, which is nice and convenient. And that the indexing transformation can be defined with get index on the sequence. So in this case, let me show this in yeah. So if we leave out the 1, we would have the name tuple, obviously. No, not named, you just have the tuple. because we didn't provide any symbol pairs here for the names. We just have a sequence of 3 elements resulting in a tuple of the result types of the 3 elements. And if we are indexing that, the first one, we will have a substring, and we'll have the indexing operation indicated in the output as that kind of indexing. It's the same thing as if we write sequence 1 like this, with the difference that in this case we're creating a function, and in the other one we're creating a the transformation parser is not getting a function, but a index object. That had a weird reason, because for some reason it was crashing Julia if I would not create a function in here. I don't know if that has vanished maybe with the later Julia version. So this, I think I prefer actually this, because it's more readable. Performance-wise, it shouldn't be a difference. There is a helper function here, which is called sSequence, simplifying sequences. They are used for flattening with the asterisks. They are exported, so if you want, you can use them. So you can see if you wrap sequences in sequence, this is just flattening them out. Exactly. So yeah, the sequence state type, I mentioned that function above. So it's match state if all field types have match state too. And otherwise, it's if it's a tuple state, it's a tuple type with a state type of parts. So a tuple of all the state types of all the parts. Or if not tuple state, it's a vector of any. In some cases, you might see a performance increase if you're using vector any, if you need a lot of backtracking, because then the vector is allocated and is written into in the state instead of the long tuple type is generated for each iteration that is matching. This depends on the number of parts and on the state types within them. So if you really want to go crazy with optimizing, you can play around with these in specific instances. You should use the profiler before you do that in order to make an informed decision in the end. And then we have the sequence result types. It's the tuple type. Either we will, I will say a little bit more about either subsequently when it comes to the recursive parsing. Either is a parser that tries matching the provided parsers in order, accepting the first match, and fails if all parsers fail. Very straightforward. It's also a constructor that is very flexible regarding the type of the options it provides. So you can create a immutable either, which is using a generated function for performance. So that is just happening when you call either with a number of arguments. These arguments will be wrapped in a parser call, so constants are wrapped in a constant parser object, and then the type parameters are computed with either state type and either result type, which basically do a type union of the state types of the options and the result types of the options. If, however, you want to have a mutable either, which you will need to create a recursive parser, you need to wrap your options within a vector. The elements within the vector will also be wrapped in parser, and the type parameters in this case will also be computed. This might not be what you want. Sometimes if you want to create a recursive parser, you will later add options. And in order for the options to be valid in either object, they need to have a compatible state type and result type, which will be checked. And if it's not working, you will get an error. In that case, you can create the or provide the state type and the result type as type parameters on the call to either. So if you call either t, you will actually create a mutable either with a vector and that result type. I'm not 100% happy with the current syntax for either, I must confess. Yeah, because of this, for the immutable part, it's trivial, but for the mutable either, I think, yeah, if you have any feedback on a streamlined way to express state types and result types in that case, if you don't like the way it is right now, I'm appreciating your feedback. So the either parsers can be extended with push and push first. We will see that later after going through all the constructors, after having gone through the assertions. Assertions we have seen. Let me see if there is a question. Oops. Yeah. Is an atomic part in a sequence treated as having a match state or a tuple state? That's a very interesting and good question. Actually, I have been treating it as a match state for a while, but then changed it recently in order to if you for the matching, a match state would suffice, but you want to transform the match of an atomic parser if you want to get the result. And for the transformation, you will need the state again. So if I would store the state of an atomic parser as a state, I would need to recompute the state, which is obviously possible. But I decided now to change that in the implementation in order to yeah, not recompute the state in the moment I'm transforming, or I'm actually using the state tape in order to produce a result. And then there's another intricate detail here, because there are several state types that worked quite well for optimization, and in this case, well, for example, when you're matching a constant string, you could use a match state. But sometimes it's easy. It's beneficial to store the number of character units with the state. So you would have a state that has no further iteration, but you have a certain length stored with the state. And sometimes you just need that. The technical background is we will see that later, left off and right off. So the point is moved quite a lot during searching for matches. And if you need to move through a lot of states in order to adjust point, that's obviously consuming a lot of time. So sometimes you just know how long the state is and move the number of character units that are stored additional to the details of the state. So these state types are available. Basically, for most of the parsers, you can just plug them in. This is also something about the beauty of the multiple dispatch in Julia, that you actually can just say, okay, I'm having this parser here, and I actually just want to improve it a bit because I'm having a lot of seeks in the string, and I want to use a state that is wrapping the original state within an object that encodes also the number of character units. Okay, I hope this has answered the question with the atomic. I will get back and see if it's okay, it's answered. Okay, assertions. They are actually, I mean, just straightforward, like in regular expressions. You have at start, which is only really useful when you're using it in a match, because the semantics of parsing means you require it to be at the beginning. But let's just see this. So so this will match, obviously. Oops. Sorry. And kernel. Okay, this will take some while again. So the idea is that if you if you have a parser that is ABC, and you use it as a callable, it's used with a parse function, expecting that you start in the beginning, which means it will not work if you remove the first part. So it will say no successful parsing. But if you would call match on that, it will obviously match the second part. So let's assign that. Oops. Let's actually look a little bit. We have been talking so much about states. You can see this has actually match state. So it's just matching. Let's change the A into a repeat. In this case, you would have stored the number of repetitions as a 1 here, which is just a 1 because the inner state of the repetition for the A is just a match state, and if it's just a match state, the state of the repetition is just the number of matches, which is different than when it's a more complicated state, obviously. But you would also have the start, which is here just at the 3, right? So that's all right. But if we would now add the at start, yeah, nothing, has no start. So then now even match will not work because it is asserted to start at the beginning of the string. Similarly, for the at end, we have seen that, but there has been this other question here with parse optional A be 42 to return false. So let me just copy that in here. Oops. Sorry. This example. So we would actually, in order for this to fail, we would need an end here. And then we have no successful anymore because it's required to be at the end. Yet, I mean, if we would just use a match here, we would obviously get a match at the end because which is an empty match. And if we would get the value of that empty match, that would again be 42, right? Because it's an empty match, and at the end there is no A, so it's the default 42. So if you want to even exclude that one, you would just add start at the beginning, and yeah, get nothing. The get function makes no sense then. Because match, semantics of match, I have taken from, or have aligned with the semantics of PCRE match. Which is return for the regex, which is returning nothing if the match is failing. That is the design decision. Okay, there are other assertions too. There is always, which is kind of a dummy assertion, never, which is also kind of a dummy assertion, but who knows? I think I actually used them at some point. Positive look behind, negative look behind. We have that. These are actually, the implementation is quite interesting. If you are thus inclined, you can look at it there. I actually refactored a package out of the implementation, which is called reversed strings, which is storing the original string but reversing the index access to it, and that is used in the look behind matchers. So it's actually reversing the parser within and the string that is matched, and that is the way this is working. But it has the same semantics as PCRE, as can be seen in the unit tests, in the PCRE's unit tests that are successful for this. Look ahead is more trivial. Both look ahead and, well, actually all assertions don't move the point, consume no input. You can, however, in the new version, get the match you have. So let me see. Yeah, well, you actually see it here. So if you would have a positive look ahead of peak, and you have you parse the positive look ahead, and then any char, you actually get the peak as the match of the positive look ahead. So if this is not peak, but anything else, a parser, not a constant parser, but a parser, you would get the match here. Obviously, for negative look ahead, you wouldn't. You just get the negative look ahead parser as the result, because it has no match. Or if it has a match, yeah, you can see it also here, negative look ahead. I'm not sure if I mixed up something now. I wanted to say for the negative look arounds, look ahead and look behind, you cannot return the parser match, because if it matches, the parsing stops at that point. So what the result type is the parser itself, the negative look around parser itself. All right, yeah, I don't want to make a break because it's already 6:10. So let's continue. A lot to go through still. Logging and side effects. You have seen the logging output, I think. So this is done with named parsers, and the constructor for named parser is with name. That is also displayed whenever you use the tree view of a parser. You can see with name and then the symbol printed there. There are some convenience markers with names. Macro will just allow you to omit the name and assign it to the variable name. And you can also do this with a begin and end, and have multiple parsers with names this way. Then there is this log names, which is actually implicitly used when you call parse with a log keyword argument, which internally is rewriting the parser. It's rebuilding the parser, replacing all the named parser instances that match the names argument, either because it's true or because the name is in a vector of symbols. And it will replace those with a call to with log, which is the next one. And with log is actually calling with effect and creating a special style, print styled effect on the current state of the match. There is actually, if you want to do this manually, sometimes you might want to, because sometimes you might want logging even though a parser is not matching. So you want to see if the parser is trying to match at a certain point and failing. And you can do this manually by using the no match keyword argument in the with log. And you can also adjust, for example, the delta, which is showing changing the characters left and right of the match in the log output. With effect, yeah, can be basically, you can plug in anything in here, whatever you want. Julia function, first class citizen, beautiful. Caging match states is also possible. There is a with memory class that is actually wrapping the string you want to match and then storing all matches for all parsers and also for like all the subsequent iterations at all points in the dictionary. There have been, well, I mean, this is a parser combinator, and parser combinator have this is not the only parser combinator out there. Functional programming languages often work like this, and they have issues with performance. And memoization is recommended as a way to improve the performance. But I don't really see the benefit in Julia. It's I think the Julia compiler is just doing all the work that typically a state machine optimization and compilation is doing for classical state machine parsers or parsers in the regular languages formal framework that allow a lot of optimization that parser combinator does not really allow, because you, well, it allows different optimizations. Anyways, let me see if there are questions. Nope. Nope. So let's look at recursive parsers. This is an example from the manual that I will walk you through in 2 different ways. And I hope this will help you if you want to create your own recursive parser. So the beginning is we will create a parser for arithmetical terms that will evaluate the expression into a rational number. So the evaluate function is just for the mapping and the evaluation. So you can just see it's like taking a tuple with a start value and then operations and values in a vector. If you remember, before we had the join function with the infix keyword argument, and this would be the infix is a prefix. So because the infix will be prefixed to the match numerical value, which then will be needed to, this is actually not a nice example. It might be like this. So plus and minus and 2 and 3. Oh, sorry. Okay, but this is the transformation part. The recursion part is the matching part, the parsing part. So term expressions are sequences of subterms interleaved with operators, right? And subterms can be several things, and they can be recursively nested. Either is used for recursion, and this one is the constructor for a mutable either, where you're just saying the result type will be a rational of integers. And the state type of subterm will be actually any. Okay. This is because, yeah, if you think about it, since they can be infinitely nested here, the state type of a recursive parser is typically to be any. A term can be an addition or subtraction or multiplication, division of subterms. Yeah, so you have these, I don't know how this is called in English. In German, it's Punktvorstrich. So it's the arithmetic rules of operator binding. Priority, I don't know, sorry. So a subterm is either an integer or a nested term in parentheses. So let's look at this. So we could have a multiplication term, which is comprised of subterms that are joined by asterisk or a dash. And we have a term that is actually several multiplications separated by plus or minus. And an addition or subtraction might be in parentheses for using it in a multiplication, but executing or evaluating the addition first. So basically, what we have then is we have this subterm that we created, which was completely empty. It was an either, where we only said it will have a result type of rational integer. And this subterm now might have a parenthesis, which means we have a term in a multiplication that is actually an addition, for example, or we just have an integer. So that is the way we are pushing here options to the either parser subterm, which then is responsible for the nature of it all. So let's look at subterm now after executing the lower part. Move this down here. So in the display of a recursive parser, you will typically see somewhere branches hidden, because that is where the subterm part is actually repeating. So let's actually wrap this in syntax. So then now you have here terms, multiplications, and oh. That was a bit too much. So yeah. Now you will have the different parts named here, and you can see that the name parser for multiplication is actually not displaying its branches because they have already been displayed. So no worries if you're having a recursive parser and want to see its details. It's possible without Stack Overflow. That is done with a dictionary and also with this parser rewriting thing. Actually, no, it's similarly done. So that is one way. So again, you create an either, provide a result type, and call it with a empty any array in order to hold the subparser options that you push to that either parser. The second way is a little bit more syntactic sugar. Literally, it's using the syntax macro. So in this case, I'm already adding the numeric parser, the text parse numeric, initially to start off with. This might become a problem because if this one is indeed the first parser, you would get a stack exchange, a stack overflow exception. No, you wouldn't. Why wouldn't you? No, you wouldn't in this case, because it's not really left recursive, because you have the parentheses there. Anyways, the next part. So here we have these two pushes. So this push is independent of subterm, so I don't need to define subterm in order to define the numeric parser, but I need to define subterm to define term, parentheses, and term. So I start off with the one I can define, and then I can add the parentheses with that for syntax. So I have syntax for parentheses in subterm, meaning there will be the option parentheses, so syntax for option parentheses in either subterm. Subterm is that either, and then you have the typical Julia construct where you have the body of that code block, and the result of that code block evaluation is just the sequence of these adds, and this one will actually be assigned the name parentheses. So these are the two options currently to write a recursive parser. And again, I mean, this is from the example. I think I will skip this. You have, well, actually, the parenthesis here is missing because the name is only provided. All right, let me see if there are questions for this. Oh. Okay. The benchmarks, this is also, I will just skip this because this is in the documentation and we only have half an hour left. The pushing is, and the push first is documented, of course. So now let's look at the EBNF support. So I wanted to have this complete, and I'm very sorry that I do not have it complete. For me, there have been quite some uncertainties manifesting into surprises in the last year and month. So what I want to show you is a draft of that EBNF parser, and I'm very happy if you want to invest time and resources to collaborate with me on this. The issue with what the EBNF support has two parts. The first part is parsing the EBNF syntax. So EBNF is a parsing language. This is, for example, a typical or one dialect of EBNF. So you would say an expression. Whoops, sorry. An expression is either an expression plus an expression or a number. And a number is, in regular expression syntax here, from 0 to 9 repeatedly. So this language would describe this kind of additions, right? And it has a left recursive pattern because you see this expression is repeated here. And if you would define such a parser as is in a parser combinator or combined parser, you would get a stack overflow error because the expression is trying to match the first option. Matching the first option, it would try to match the expression. Matching the expression would again try to match the first expression, and so on ad infinitum. So this pattern needs some extra care in a combined parser or in a parser combinator, in a functional way to parse this. This left recursion needs special handling. On the other hand, the part that is reading and parsing the EBNF language itself, so everything else in a sense, that is already done. And for the left recursion, I actually experimented successfully with it in a way that it's basically using the memoization parser and noting a block at the position. And when it's recursing further in, it's realizing that it has a block recorded at the position for this parser. But then I wasn't happy because one of the strengths of combined parsers is that it can iterate different valid parsings for the same string if the syntax or the parser is ambiguous. So, for example, in the case here, for that language, expression plus expression, so typically you would have left recursion, but this would also be a valid parsing in the sense that we would not couple the first two and then with the third and then with the fourth, but rather couple the last two and then from right to left. So I want to iterate all those, I think, and that was turning out to be buggy, so I didn't publish it. If you want to participate, you can see, let me just switch briefly. The screen share to another tab. Okay, so just to briefly show you the BNF syntax, this is basically from the manual. It's straightforward. You have your different symbols and ethers. The interesting part comes further down, where you see, so here, for example, where you see the mapping from whatever we match to saying, okay, this one now needs to be an optional, or this is the syntax for a repeat, right? So then parser is working quite nicely, and it's parsing all those different examples, but the left recursion part needs a little bit more work. Okay, now let me see. Are there any questions? No. All right, so let me switch again. Share screen. So let me briefly just give you the highlights of the PCRE compliance right now. Many things we already have shown several times. One thing that is, I guess, interesting is that the RE macro handles, for example, named groups nicely, in the sense that they are used like with name or at syntax macro. And you can use the match interface with an indexing by the name. This is only possible for the PCRE created parts, because these captures in PCRE require a very specific handling, and it was quite cumbersome in CombinedParsers to accommodate for it, because yeah, well, it's just not the same system. So, for example, a capture is captures have numbers of the number of occurrence. Optionally, they have names. If a capture is repeated or repeatedly matching, only the last match is actually recorded, and then it can be used for checking if the match is repeating. So you can have well, I'm sorry, my language is losing me. What is it called? Not a subroutine. Well, but basically, you can instruct PCRE to check if at a certain match the pattern of a capture that has already been matched is repeating, and it's only storing the last match of that capture. And also for the name, if that would repeat, that's also the same issue. And I try to be really feature compatible and compliant with PCRE. So the RE string macro, when it creates a combined parser for that expression, you can see here it is a sequence, but it's a regular expression combinator with 3 capturing groups. So there is a state handling going over all of the matching process that is done here, and that takes that makes things a bit slower than writing things really as a combined parser. The features of the PCRE compliance are quite nice. So it's unit tested on the unit tests of PCRE, and most of the tests are going okay. There are some not supported features, like accept, skip, commit, then, and prune. These are features I didn't see why they would be worth the effort to implement right now. If you need them, if you really need them in combined parsers, probably the easiest way is to write a combined parser that does the same thing instead of using a complicated PCRE expression and using combined parsers to do something similar. And there are limitations with the captures and look aheads and look behinds. But apart from that, we are feature complete. The nice thing is when you're using the regular expression string macro and you don't use captures, you will not have what I showed here, this regular expression combinator with 3 capturing groups. So it will be really as fast as writing it in combined parser constructor syntax in Julia. So it's really nice to be able to combine certain parts, writing certain parts as a regular expression and certain parts as a combined parser. That is the reason why I think the completion of the BNF parser will be a very nice thing, because then you really can combine different parser languages even one more. And also, since I want to generalize it with that memoization idea, it would catch cases where you are writing your parser badly, such that it has a left recursion, which is currently not detected. It might just currently throw a stack overflow, which is ugly and can be tested and can be wrapped automatically by rewriting the parser in such a memoization element. All right, so we're slowly closing to the end of the workshop. One thing that I wanted to go into a little bit more is the parametric types and dispatch optimization, because parsers as well as states have custom types, and this allows method dispatch to insert fast matching code for special cases. And a recent addition to the package is similar, for example, to, I think it's JSON3 package, has lazy access to the parsing of a JSON document, meaning you don't need to create the JSON representation for a full document, but you can parse a longer document and say, I only want the 20th element created in memory. And the tape or the state is used to find exactly what you actually want. So if you, it's already working on a subset of things, but it's not easy to solve in general. I will show the code, and then we can discuss a little bit in detail why it's not trivial. So, for example, if you have a repeat of any character and you have some 1, 2, 3 separated by dots, the state of that is a 7 because it's 7 times matching any character, because the any character has matched state type match state. And if you want the third match within the match of that, you will have a different parse match. So, sorry, I will just, let's look at this. So you have a parse match 0, 1, 2, 3. And here you have a parse match of 1. So let's see what exactly is stored in that parse match. You can see there is a matches iterator in case you have want to really iterate all the different matches, like with parse all. And then the matches iterator has the parser, which it obviously needs, the sequence, and from until. So typically, by default, that is starting at the first character, and it's trying to match until the end. Or, yeah, trying. It doesn't require it. And then you have the current start and stop and state. So you can see for this specific match of the whole document, you would have a state of 7, a start at 1, and a stop of 8. And if you're now indexing that at 3, you will have something very different, because here you have a parser, which is the outer parser, the repeat of any character. And in here, you would have just the inner parser, because at position 3, obviously, you need to unroll this state, which is just 7 at position 3, which means there is a match state, because otherwise the state of the repeat would not be an integer, but the state of each individual element in order you can backtrack correctly. So here you will have the state of a match state appropriately. So if you would, if you want to get what's getting out there, you would get the Unicode ASCII character. Similarly, if you would have a sequence, let's just again look at the match. So we have just 4 elements in the sequence. So the match would be from 0 to the dot after 1. And if we would want this, well, let's use the third, and this would be, oh, I broke something in the last minute. Oh, 1 second. Okay. Revise is your friend. So now this will be the one. And if you look at the representation of that, it will be very similar here. It will be the match state, and the parser will be Yeah, just also a match state. Okay, how is this done? Let's look at this. I'm not sure if I can. No. Change the sharing of the screen. Okay, this is the code. So we're overriding base get index on the parse match. The parse match has type parameters. And this is the general case. So if there is a transformation, the laziness is not easy to do because the transformation can be arbitrary, and I want to do a get index on some transformation. So basically what we're doing is we're printing a warning and getting the evaluated result and calling get index on the evaluated result. So this will not be lazy. But if we want to get the index of a parse match of a sequence, what we actually do is we take the stop, the end of the match, and then we know that since the sequence is matching, the last part of this, so the part at the last index position of the sequence is matching. It also will have so basically what we need to do is we need to walk back from the rightmost parser within the sequence to the second rightmost until we are at the index position I. So we're basically just calling this function left off repeatedly until we arrived at position I. And then we create a new parse match with the inner parser and with the state at position I, and with adjusted start and stop values. And similarly, the same thing for repeat. What's interesting is studying a little bit how the internals is working here. We have this left off function that's used a lot for this jumping back and forth over states within the sequence. And for example, in the case of repeat, we have a function that is an internal function that is called poplast, and that is handling all cases. In case the auto state is an integer, the exclamation mark changing that integer is a little bit misleading, but it might be a vector. And then the auto state is removed from the last position and returned here. So in this way, you can jump to the left in that way. And then in case you have a join substring, an exclamation mark, obviously, if you call get index, you want to index that string match, and you can use that. And if you have a default wrapped parser, which, for example, a named parser or a parser with effects, you just pass the idea on into the parser that is contained in the parser, in the wrapped parser. Okay, yeah, that is lazy evaluation that is recently added. Now I will look at the screen if there are any questions. No. Okay. So let me switch again. Oops. Here we are. If you want to have more details about how to write your own parser and what the internals are for iterating and jumping in a string according to the state from the right of a match or to the left, or from the left of the state to the right, there is a custom palindrome parser example in the documentation that might be of educational, because it's a parser that is easy to understand but not trivial to write, and not trivial to actually read or see that a certain regular expression is matching a palindrome. Yeah, no, I will not switch to that now. Otherwise, I will get out of the time allotted. So let me just highlight a few more things that I think are really cool about CombinedParser. One thing is prefix trees. That has already been there last year, but it's still cool and fast. So, for example, if you would have a regular expression that is either one of 5-letter strings in a set of 5,000 of those strings, you could join them with the pipe symbol. And if you would benchmark them, you have a runtime in the microseconds. If I tried using 10,000 strings, and this fails in PCRE, but CombinedParser dispatches and either with a vector of abstract strings to create an optimized, either based on a tree implementation of a character. So this is not a state machine, but it's immensely fast. So you can see that this either on that huge string array, if you're using match to check if something matches any one of those strings, is how many times faster? 500 times, I think, is this. So this is quite nice, and this is a good example of how you can, or how combined parsers can be optimized due to the great features of multiple dispatch in Julia, because in a special case like this, where you have just a set of abstract strings that might match, you can plug in your custom implementation for that. So let me get to the summary. I have showed you the regular expressions. They are PCRE compliant and a nice building block, interoperable. I've shown you the design and standards. The brevity and type inference, I think, are most mentionable in my opinion. And you've seen the iteration combinatorics and the custom parser API. The performance is good. In the very beginning, I have shown that more than half of the PCRE unit tests actually run faster with CombinedParsers.pcre. That is all due to parametric types dispatch optimization. Generated functions are used heavily, prefix trees, and a bit of minimization. I think this makes CombinedParsers a really good fit for use with the remote channels in order to design message broker systems. I would love to see actually a remote channel to grow and get that kind of functionality to write the events that go through the channel in partitions in a distributed fashion that can be replayed, because then I believe Julia could play a role in that part of the industry, which is, I guess, not the first area of industry that Julians think of when they think of industry and Julia, because Julia strength right now is mainly on the area of scientific computing, that is numerical methods. And with the CombinedParsers package, I think I introduce a way to use the Julia language with much benefit, and especially the Julia features of optimized compilation with multiple dispatch and parametric types that create such a fast code in cases where processing is complicated, like it is in parsers. And if you can seamlessly integrate code for parsing with code for processing in a pipeline, and Julia compiler is compiling and optimizing that out, I believe the prospects are just great. So let me see if there are finally any questions. One new question. Oh yeah, where can I find org mode parser? I will publish that, but it's not ready. So it's not feature complete. I have used it for my own org mode files, which are extensive and a lot, and it's by far not feature complete. But if you're interested and want to participate in making it feature complete, I'm more than happy. Also, the Wikitext parser is already published. All right. Any other questions in the last 3 minutes? So what's next? I really want to remove the character name references in the syntax in order to better reflect that it actually can parse any kind of vectors. Also, what would be a nice thing after doing the EBNF infinite left recursion stopping would be to look a little bit more in optimization, and especially prefix extraction and making parts of the parser as far as it can go into a tree, like the character tree that had this great performance, and also generalizing the parser to streams that might be discarded after matching at a certain cut point. That is a feature that fastparse in Scala actually has. So you can basically just have a repeat on a stream, and the stream is caging while it needs to backtrack. And once it's has a certain result, it can cut the stream and give it to garbage collection. Now let me look for 2 more questions. Do you offer example of code? So new there are some examples, code examples in the manual, on the documentation. If you need something more specific, please write an issue. I apologize. In the last year, I have not been very good with emails and on GitHub, because there was just a lot of stuff going on. But I hope I can improve that. And if you want to invest in this kind of stuff, I'm more than happy. Apart from left recursive grammars, can combined parsers be used for implementing simple EBNF grammars? Yeah, you should be able to do that straightforwardly with the example that is actually in the GitHub tests directory. Get in contact with me on GitHub. All right, so I think the time is up. Thank you very much. I hope you like it. I'm looking forward to being in contact with you. Bye-bye. Okay, no more questions.